We saw in the previous video how you can try and solve differential equations by rewriting the left-hand side as the derivative of the product of two functions, a function of y and a function of x. In this case here, this method will not work, and I'll show you why very quickly. It won't work because, if you remember from the last video, when you do differentiate this, we get g dash y times dy by dx times f of x plus g of y times f dash of x. So that is just differentiating this using implicit differentiation and the product rule. Then we tried to compare this to that question to try and figure out what g of y and f of x were. So if I compare this up here, I can see that g dash y f of x has to be 1, because I've got a dy by dx here, a dy by dx here, so these bits must be 1. Then comparing this to this, I see that g of y f dash of x would be minus 4y. So then, comparing here then, I'm thinking that the g of y function here, that's the function of y, so that could be the minus 4y, which if that were the case, that would mean that this would have to be 1. Minus 4y times 1 would give the minus 4y. So I'm thinking that those could be possible functions. If that was the case, g dash would then be minus 4, f of x would be x, so just differentiating this, integrating this. Then I think, okay, well, if I multiplied these two things together, would that give me this? Would that give me g dash y f of x equals 1? Well, no, obviously not. Timesing these two things together would give minus 4x, not 1. So this method will not work for this question. So the question then is, how do we integrate something like this? What we do is we use something called an integrating factor. And I'm going to multiply all the way through by the integrating factor, which will then allow me to use this method. So, integrating factors can be used with questions that look like this. You can see this does look like the previous example here, where we've got dy by dx plus p times y. Now p is just a function of x, equals q, where q is another function of x. So we can use integrating factors whenever we have a question that looks like this. The integrating factor itself is this. It is e to the power of the integral of that function with respect to x. So let's repeat that. The integrating factor is always e to the power of the integral of that function with respect to x. And I'll show you why that works. So like I say, we are going to multiply all the way through by this factor. Now at the moment that looks quite complicated, but you'll see in a minute, this actually most of the time simplifies really nicely. Anyway, so if I multiply each of these terms by this, okay, so I've multiplied the dy by dx by my integrating factor. I've multiplied the py by my integrating factor. And crucially, I've also multiplied the q by the integrating factor. That allows me to rewrite the left-hand side as the derivative of y times the integrating factor. This is the reverse product rule, just like we did in the last video. Just to prove that that works, if I were to use the product rule on this, if I were to differentiate this out, let's just do a quick check. So I differentiate the y function and get dy by dx times this function. Then I would differentiate this function. Now we know that the exponential differentiates to give the exponential, but then by the chain rule I have to multiply this by the derivative of the inside function. And when I differentiate the integral of p, I'm going to get p, because the differentiation and the integration will cancel out. And hopefully you can see now that this is the same thing as this, which means that we can rewrite this like this. So once you have multiplied through by the integrating factor, you will always then be able to rewrite the left-hand side as the differential, the derivative of y times the integrating factor. Over on the right-hand side, you've just got the same thing. You've got the integrating factor times q. But most importantly now, we are then able to integrate both sides with respect to x. And like I said before, this will always be a nice simple function, and this will be nice and easy to integrate from there. So that is your method. That is how we solve differential equations using an integrating factor. So let's go back to that question that we saw a moment ago, which was this one. So we can see that it is already in this form, and we can see that our p function is -4, which means that our integrating factor is going to be e to the power of the integral of -4 with respect to x. So I'm just replacing the p function, the -4 from here. The integral of -4 with respect to x is -4x. So my integrating factor is e to the -4x. So I am now going to multiply each term here by e to the -4x, which gives this. Timesing this by e to the -4x, this by e to the -4x, and timesing this by e to the -4x. Then, the left-hand side, I can rewrite all of that as the derivative with respect to x of y times my integrating factor. And just to check that that works, if I differentiate this with the product rule, I get dy by dx times e to the -4x plus the derivative of this times y. The derivative of this is e to the -4x times -4, which is that. So this is the same thing as this. It will always be the case where you have the derivative of y times the integrating factor. On the right-hand side over here, I have just simply used index laws to add the two powers together to get that. I can now integrate both sides with respect to x. So integrating the left-hand side will just give me what's inside the brackets. Integrating the right-hand side. Integrating the exponential will give the exponential, but also remembering that I have to divide by -3 by the reverse chain rule. Don't forget the constant as well. And then the only other thing I might do here is I might multiply all the way through by e to the 4x. If I multiply this side by e to the +4x, then those are going to cancel out. Oops. So then I'll just have to times e to the 4x here and e to the 4x here, which will give me that as my final answer. Just to tidy that up a little bit at the end. By the way, you might notice, you might have asked yourself why I didn't do a +c here when I was integrating for the integrating factor. The reason I didn't do that is because I could then just rewrite that as e to the -4x times e to the power c. And e to the power c is just a constant. So when I then times through by the integrating factor here, I would then just end up with an a, an a, an a. So I could then just divide through by that constant. So that's why you don't need to worry about the +c when you're doing the integrating factor. Right, let's do another example. In this case here, remembering that I want my differential equation to look like this. So I want to have just the dy by dx here. In this case here, I've got a cos x at the front, which I don't want. So my first job is going to be to divide all the way through by cos x, like that. So dividing through by cos here, dividing through by cos here, we'll do sine divided by cos, which will give me a tan. And then cos to the power 4 divided by cos will be cos to the power 3. Right, now using my integrating factor, remembering that the integrating factor is always related to the p constant. It's e to the integral of p with respect to x. In this case, my p is the 2 tan x. So my integrating factor is going to be e to the power of the integral of 2 tan x with respect to x. Now we know that tan integrates to be ln sec. So 2 tan x will be the integral of 2 tan x will be 2 ln sec x. I can simplify this because obviously using the laws of logarithms, I can take that 2 and put it as a power up here. And then what's nice is that e to the ln cancels out and I just get left with the sec squared. So my integrating factor is sec squared. So if I now multiply through by sec squared, I get this. So times here by sec squared, times here by sec squared, times here by sec squared. Now I know this left-hand side here can be rewritten as the derivative of y times the integrating factor. Y times the integrating factor. And again, you can just check to make sure that works by differentiating this with the product rule. When you differentiate this with the product rule, you do get this. I'll let you check that for yourselves. On the right hand side over here, I know that sec is 1 over cos. So sec squared is 1 over cos squared. So cos cubed times 1 over cos squared will cancel out and just give me cos. I can now integrate both sides with respect to x. Cos integrates to be sine. And then to tidy this up at the end here, I can, because I know that sec squared is 1 over cos squared, I could multiply through, because I know that's a 1 over cos squared here. If I multiply both sides by cos squared, that will simplify that. So timesing through by cos squared, I probably should have chosen a different letter for my constant of integration here to avoid the double C. So maybe I should have used an A there. Not that it matters too much. Hopefully you can see what I've done there. Anyway, last example on this. We're going to have a look at this one. So same idea as before. I don't want that x to be there, so I'm going to divide through by x as my first step, which gives all of that. My integrating factor then is going to be, well, my p is 5 over x. So my integrating factor is going to be e to the power of the integral of 5 over x with respect to x. 5 over x integrates to be 5 ln x. Again, similar to before, I can now take this 5 and put it as a power here. The e and the ln cancel out and I'll just get x to the power 5. Multiplying through by x to the power 5 gives this. And you could do a little bit of simplification here if you wanted to. Obviously, that's just going to be a power 4 now there. That's going to be a power 3 over here. So you could do a bit of simplification here if you wanted to. But most importantly, this side can be rewritten as the derivative of y times the integrating factor. Again, just use the product tool to make sure, satisfy yourselves that when you differentiate this, you do get this. And obviously, like I said up here, the right-hand side simplifies to be this. Now we can integrate both sides with respect to x to give this. And we can integrate this with by parts. So say u equals ln x, v dash equals x cubed, and so on. I'm not going to do integration by parts here. Yeah, the key thing really then is to, when you've got a function like this, when you have a differential equation like this, rather I should say, your integrating factor is always going to be e to the integral of whatever this function here is. You are then going to multiply all the way through by that, at this stage here. It's really important you write that stage there. The left-hand side can always be rewritten like this, y times the integrating factor. The right-hand side will be the same here. Just one point on this, a lot of students tend to skip this step because they know they can use the shortcut of this. What a lot of students do is they think, okay, I found the integrating factor now, so I can just write down d by dx y, the integrating factor equals, and they forget that the right-hand side here also gets times by the integrating factor. And then they make mistakes, and then obviously the rest of the question all goes wrong then after that. So this stage here, where you are just multiplying each bit of this by the integrating factor, is crucial. So don't forget to do that.